Hello, everyone. So you are welcome to part 3 of this class, generalized material balance equation. It has been quite an interesting one. Starting from the basics, we look at the reservoir types, GMB, and we have also looked at the Schilthius material balance equation assumptions and derivation. So in part 3, we'll be looking at the Havlena and Odeh. It should be Havlena. Havlena, there's a L here, and Odeh derivation. Okay, so I'll be running to slide 35. Go with me to slide 35. Um, okay, here the equation 25 and 26, where we derive the general material balance equation showing that our F underground withdrawal is a tank model and it equals the energy of the reservoir system, um, the oil and gas expansion, component, the gas cap expansion component, um, the connate water expansion, and the rock compressibility, and the water influx. Okay? So for equation 25. And then for equation 26, when you have your water injection and gas injection component present in your reservoir, water injection and gas injection components present in your reservoir. Okay, so right now we'll be going to the Havlena and Odeh. Havlena and Odeh expression of the general material balance. They did this in 1963, published their work on the Schilthius material balance equation, and they simplified the general material balance equation. Okay, so from our equation 25 and 26, Havlena and Odeh modified it. So here we see the F, they retain the F as the underground withdrawal. N is common to our component A, B, and C. Okay, so N as a subject here. This is the oil and gas solution gas expansion. This is the gas cap expansion. This is the rock and connate water compressibility. And this is the water influx. So quite simple. So you have the NEO, MNEG, and NEFW. Okay, and then the water influx. So in case where for some text, this is included, I've mentioned it in the part 2 of this video, where you have the water injection and gas injection pressure maintenance, you have your BW, and you have your BG gas injection, BG injection. So you have the water injection component and the gas injection component added to your WE, water influx. And please don't forget, because I may ask you in your exam, why is this model considered as a tank model? Why is it zero dimensional? Why is it considered a tank model, zero dimensional model? Okay, so the addition of all this gives us the subtraction of your uh, left hand side, your F, from your right hand side gives you 0. It gives you 0. So you have your underground withdrawal, okay, and it's based on the law of the conservation of mass. And then you have the energy of the system. So when you have a withdrawal from your reservoir as a result of your F, there's a pressure drop as a result of your F, your left-hand side responds, everything on this left-hand side, depending on the drive of your reservoir. I believe you are able to connect now. We did a lesson on drives, the different types of reservoir drive systems that we have. So we're able to connect now. So depending on the drive of the system, whether your system, your reservoir system is driven by expansion of its oil and its solution gas components, or your reservoir has a gas cap and is driven by the gas cap expansion, or your reservoir is driven majorly by the components, the connate water expansion and the rock compaction, which goes on within the system, or you have a water influx, or you are carrying out a pressure maintenance system, whether through water maintenance, water injection, or gas injection. Any one of them going on or combination of them must respond to balance this energy of the underground withdrawal, such that when you remove your right hand side from your left hand side, the balance will be zero. That is the tank model, okay? And it is based on the law of conservation of mass. Okay, so you can go back to revise your law of conservation of mass. You may want to state it in order to buttress the point of your tank model. And you should also be able to state your equation 27 and your equation 27A. And tell me the difference between your equation 27 and your equation 27A. Okay, so let's go back to Havlena and Odeh, great guys in 1963. They made this equation 25 and 26 quite simple for us. Okay, so once a straight line has been achieved, so what they say is this arrangement in equation 27 and 26 will form a straight line. The plot will be a straight line, and once it is achieved based on the matching observed production and pressure data. Don't forget the requirement for MBE. There has to be a history data. So production data, pressure data. The engineer has then built a suitable mathematical model to describe the performance of the reservoir. So Havlena and Odeh made it possible for reservoir engineers to be able to describe the performance of their reservoir, the size of the gas cap, the N, even your fractional recovery, which is your MP over N, okay, your fractional recovery. So they made it very possible for all this to be estimated. Okay, so let's go on. From our equation 25, you remember equation 25, okay, the almighty equation 25 and 26. Okay, that's your F equals to A plus B plus C plus D. So the unknowns in those equations, you have your original oil in place is unknown, okay, because it hasn't yet been estimated. That's the O high P, okay. Your water influx also needs to be estimated, okay, if it is present, and then the size of the gas cap, okay, the size. These are the three almighty unknowns in your material balance. So easily from your equation 25, you can make your N the subject, okay, you can make your N the subject, and then you have this. So if you rearrange the equations, you know N is a common factor to your both your right hand side and to your left hand side. Okay, so if you bring in the N out, you will have this. You are now quite familiar with this numerator, which is your F, underground withdrawal, and the remaining of all this is your what? Is your the equations on your right hand side. Okay, the equations on your right hand side. Okay, so you remember this oil expansion and its solution gas, the gas cap expansion, and the compaction due to connate water compressibility and rock compaction. Okay, sorry, connate water expansion and rock compaction. Okay, and then you bring your WE to the other side of your F so that you can have your N here. Quite simple. That's your equation 28. Okay, so can you do for WE? Grab your pen. You can pause the video. Make WE the subject. See what you have. You can also try for your gas cap, your hem, and see what you have. Okay, so let's go on. So Havlena and Odeh expression of MBE, each term on the right-hand side of equation 25 accounts for method of fluid production, and each term on left-hand side represents an amount of hydrocarbon or water production. I believe you understand that. From the right-hand side accounts for a method of fluid production, that's the energy, and from the left-hand side, that's your F, okay, represent an amount of hydrocarbon or water production. So hydrocarbon is your oil, remember, your NPBO, WP, WP, BW, and also your gas. Okay, so you have your N into RP minus RSBG. So you have all that on your left hand side, and then the ones on your right hand side account for the method of the production. That's the energy. So I believe you can connect all the classes now from the energy drives to your material balance, and then we are coming down to Havlena and Odeh expression. Then your HEHO describes the expansion of oil and its originally dissolved gas expressed in terms of the oil formation volume factor. Okay, so this is showing your HEHO. This is your HEHO. Okay, then when you have BT is two-phase formation volume factor. Your HEHO will be BT minus BTI. So you know your BT. So your if you rearrange this, you have your EHO to be BT minus BTI. So in terms of two-phase formation volume factor, BTI equals BO high. I believe you can remember that from your BO pressure plots. Okay, your BTI equals BO high because um, it is a two-phase formation volume factor, and then your reservoir is already in the saturated state. So your BOI is actually a BTI because it's already in two phase. There is gas and there is oil present. Okay. Uh, so you have your EG. EG, what we are defining now is what we have here. I went back some few slides. This equation 27, we are trying to define your EO, your EG, and your EFW. You know your HEB, gas capsize. Okay, so all of this in equation 27, the EO, EG, and EFW is taken from equation 25. Okay, I've explained that is a summary of summarized version of your equation 25 and your equation 26. Okay, so if we go back to this slide, your EG is the term describing the expansion of the gas cap gas, which you have here. So your EG is BOI BG over BGI minus 1. Okay, and when you have your two-phase formation volume factor, where your BOI equals BT high, so it will be BG over BGI minus 1 multiplied by your BTI because it's already in the saturated state. Okay, so it can either be this when it is in the saturated state, or this if it is in the saturated state. Okay, then your EFW represents the expansion of the connate water and reduction in the pore volume. Okay, that's your EFW. So you have you have this already. You have this already. I'm sure you understand what this is now. Okay, and then you have your WE, which is your water influx. And don't forget on your left-hand side, which is your HEF. You are familiar with this now, which is your HEF. Your HEF, okay? Your HEF. And then in terms of your, if it is a two-phase, if it is in two-phase, okay, you have your gas and your oil. What happens? It becomes your HEF will be your BT plus RP minus RSIBG. You have your NP here. Please don't forget this is an error somewhere around here. NP into BO plus RP minus RSBG plus WP BW. So your BT will be your BT. This is the definition of your BT is BO plus RSI minus RSBG. This is the definition of your BT. So if you slot in you slot in into here, what you have is this. Yeah, what you have is this. Okay, BO plus RSI minus RSBG. Okay, that's your BT. So you can bring your BT. If you make BO your subject, you will have BT minus RSI minus RSBG. Okay, so your HEF will be BT plus RP minus RSI BG plus WP BW. Please don't forget your N somewhere around there. Okay, so Let's look at the applications of Havlena and Odeh. Applications of Havlena and Odeh method is a straight line method, requires the plotting of a variable group versus another variable group within the variable group selection, depending on the mechanism of production under which the reservoir is producing. So whether a variable group from your left-hand side or from your right-hand side, okay? Or you make uh, a subject based on the straight line equation y equals mx plus c, uh, you are able to plot your variable group y against x, okay? Y against x. And then you are able to calculate whatever your slope is. So your slope will be anything. We'll see in subsequent slides, okay? The straight line plot provides the engineer with valuable information that can be used in determining the following unknowns. You have your initial oil in place. I mentioned this earlier, your gas cap size, your water influx. You can also identify driving mechanism. We'll see that shortly, and your average reservoir pressure. Okay, for your average reservoir pressure, as you go on your reservoir engineering journey, your reservoir engineering 2 and your advanced reservoir engineering, for those that want to take a postgrad, you will still see some of the water influx models, driving mechanisms, average reservoir pressures, how they can be estimated. Okay. So let's look at case 1 of the application of Havlena and Odeh. What exactly did they do? We have seen that they came up with this equation, this simplified equation, that's equation 27. And we have seen what each of these stands for in our equation 25. Okay, so you may not fully understand this video if you did not listen to the part 1 and the part 2. So I encourage you to go back to part 1, part 2, so that you fully understand what we are talking about in this part 3. Okay, so volumetric undersaturated oil reservoirs. So you know what volumetric is now. No presence of water influx, okay? There is no water inflow into your reservoir, though there is a connate water. So you have to understand the difference between your water influx and your connate water. Your connate water is a natural water, okay, within the interstitial pores or microscopic pores of your reservoir. It is a natural water which exists within your reservoir system. Ideally, your saturation, your total saturation in your reservoir is your SO plus SG plus SW. That's saturation of oil plus saturation of gas plus saturation of water. Where gas is not present, that would be SO plus SW. Where oil is not present, that means the gas reservoir, that would be SG plus SW. Okay? Where gas or oil is not present, you will have SW only to be equals to 1. Okay? But you cannot have, almost not possible, where a reservoir whereby water is not present. That is the connate water, the innate water of that reservoir, which occurs in the natural existence of that reservoir, okay? And then your water influx, that's the aquifer, that's the water body that is adjoined or joined to your reservoir, okay? It's an external system on its own, but it is connected, hydraulically connected to your reservoir, okay? In terms of water inflow and then pressure, okay? It maintains the pressure of your reservoir. So I believe you understand now the difference between the connate water and the water influx into your reservoir. Okay, so when we say volumetric undersaturated oil reservoir, meaning there's no water influx, volumetric, undersaturated, meaning that there's no gas cap, okay? And if it is undersaturated, your RP equals RS minus RS equals RSI. So RS is constant all through because it is undersaturated. All the solution gas is within the oil system, the reservoir oil system, because it is still in the undersaturated state. Your P varies between your P high and a little bit above your PB. It does not even hit your PB because on your PB, there is first drop of gas. Okay, so between your P high and a little bit above your PB, okay? So that is your undersaturated state. Please don't forget your pressure RS plus and your pressure BO plot. BO plot. Okay, I'm sure you should be able to connect all these with your reservoir types, reservoir drives, uh, volumetric volumetric estimates also of your reservoirs. Okay, so um, your M is 0, your RP equals RSI equals RS, and your W equals 0. Okay, okay, so that's all we have here. And then, so what happens? Let's recall our equation 25. You know your equation 25. Let's recall it. Okay, we have it here. So what happens when your RP equals RS? This becomes 0. Your W is 0. Your RSI equals RS because it is in the undersaturated state and it's volumetric. Volumetric W equals 0. Your RSI equals RS because and equals RP. Your RP is the solution gas produced to the surface. Okay, your solution gas, that's the gas from your oil produced to the surface. Your RS is at every pressure, okay, but it's not yet produced to the surface. Okay, your RSI, that's the initial solution gas still within the body of your oil, okay, especially at that undersaturated state. Okay, so at that undersaturated state, all these are equal. Your RS equals RSI equals RP. So this becomes 0, this becomes 0, this is equally 0. Okay, so what do we have left? What do we have left? We have NPBO, this has become 0. We have WPBW, okay. We have N into BO, BO minus BO high, that's a HEHO. And then we have our gas cap is equally 0. Our M is 0. Our M is 0, so this goes as well. This goes as well. And then you have your W here, your W here, your M here is 0, so you have 1 plus 0, BO high over 1 minus SW. So what you have left here is BO high over 1 minus SW to CW SW plus CF, but your W is 0. Okay, so we have F equals NEO plus EFW. F equals NEO, okay, plus this has become 0 because this multiplies this, then plus EFW, this EFW, okay? So using Y equals MX plus C, Y equals MX plus C. N equals, if you make N subject of formula, you can have F equals this, okay? You can have F equals this. You can do this yourself, and then you see F equals this. And your F, don't forget that you have your F underground withdrawal is NPBO, what we have left here, and BWWP. BWWP, okay? And then divided by this. Your EO is BO minus BO high, which you have here, okay? And your EFW, remember M is 0, so 1 plus 0, you have BO high over 1 minus SW, and then you have CWSW plus CF, okay, at DP. Okay, don't forget your DP is P high, initial reservoir pressure minus every other pressure, okay? So let's look at application of this. You know, for the volumetric undersaturated oil reservoir, we have reduced equation 25 to this, to equation 33. Okay, we have reduced it to equation 33. You can look at F equals NEO plus EFW. So what can we make of that equation? If we look at Y equals MX plus C, Y equals MX plus C, translating it into a straight line equation. So we have F over EO plus EFW, okay, F over EO plus EFW, okay, lie on a horizontal straight line which means that the reservoir can be classified as a volumetric reservoir. Okay, can be classified as a volumetric reservoir. Just a minute. Okay, so I'll move this so that you can see the plot. We have F divided by EO plus EFW plotted against NP or time. So you'll be given NP or can be plotted against time. Okay, plotted against time. So this is your N. So if you have this straight line plot A, okay, if you have A, it implies that a reservoir can be classified as a volumetric reservoir. So it will show, we said one of the things that you can obtain from your Havlena and Odeh material balance derivation is the type of your reservoir drive, okay, the energy of your reservoir. So here, if we have this plot, if it goes on a straight line, what you have is that the reservoir is classified as a volumetric reservoir. Okay. This defines a purely depletion drive reservoir whose energy drives solely from the expansion of the rock, connate water, and the oil. So I believe you understand this now from the part 1 and the part 2. So it's showing that the reservoir is purely volumetric. And because it is purely volumetric, there is no water influx. What is driving the reservoir is basically expansion of the oil, expansion of the solution gas present within the oil itself, and then connate water expansion, and then the rock expansion. Those are the drives of this. So it is a complete depletion driven reservoir, depletion drive driven reservoir. Okay, so let's go to B. So if we have this B, what does this imply? Instead of your plot to go this straight line, you discover that while you plot F divided by EO plus EFW, don't be scared because you'll be given all the data you need for your EO, estimation of your EO, all the data you need for estimation of your EFW, and all the data you need for the estimation of your F. So all you need is to just put the data together, estimate your EO, estimate your EW, estimate your F, divide it, and then do the plotting. You'll be given the time, or you're given net production over time. Okay, so the shape of the curve versus time is highly rate dependent. Okay, so this is rate dependent. In this case, so when you have this B, okay, B, what happens? The reservoir is producing at a higher rate than the water influx rate. So that means there will be an energy deficiency within your reservoir system. If the reservoir is producing at a higher rate and the water influx rate is slow, remember there has to be a balance which the water influx produces, okay, with your reservoir. Firstly, this B, because it's not a straight line, shows that there is a water influx. And it shows that there is no, the reservoir is not a volumetrically controlled reservoir. That means it's hydraulically controlled, okay? That's why you have it as a curve and here as well. So B is showing that reservoir is producing at a higher rate and the water influx rate is slower than the rate of production from your reservoir. So we have voidage, then the pressure loss, the pressure depletion is higher because the energy of the aquifer is not balancing up the energy within the reservoir system. There ought to be an inflow of water, okay, or influx of water from your aquifer, okay, to balance the energy system of your reservoir. So what the water does is it goes into the microscopic pores where the oil or gas has been produced and then fills it up. So balancing the energy of the system. So what happens is that the plot dips downwards, revealing a lack of energizing by the aquifer. So it's showing that B also shows that for this aquifer, the outer boundary has been felt, and the aquifer is depleting. Okay, so it shows that this aquifer is depleting. The energy of this aquifer actually is depleting um, as the reservoir is being produced. So what this means is that it could be a weak water drive or a partial water drive. A weak water drive or a partial water drive. Okay, so let's look at C. So these are derivations which Havlena and Odeh actually made possible from um, simplifying the Schilthius material balance equation. So let's look at C. This is for a strong water drive. Okay, so this is also showing that the reservoir is not volumetrically controlled, rather it is hydraulically controlled, meaning that there is a water influx. There's a water drive, whether artesian or there is an aquifer adjoined to it, and it's very strong because, as you can see, as production produces, what is happening? The F over EO plus EFW is increasing. Okay, so it's showing that it's infinite acting. Infinite acting. As you proceed in your reservoir journey, you discover water influx could be finite, your aquifer could be finite acting or infinite acting. Okay, it is finite acting when the effect of the oil water contact, okay, the pressure exchange or the energy exchange at the oil water contact or aquifer oil contact is felt at the boundary of your aquifer. So once that effect is felt at the boundary of your aquifer, there's something that is called the aquifer boundary. You still get to know in your probably your reservoir 2 or your advanced reservoir engineering. So once it is felt, it shows that the aquifer will deplete with time. Okay, but when it is not felt, when the energy in between the aquifer oil boundary, okay, aquifer oil boundary is not felt at the boundary of your aquifer, okay, when it is not felt at the boundary of your aquifer, that means that aquifer is strong and it is infinite acting or infinite acting, okay, has an infinite acting behavior. And it shows that it is a strong water drive system. That reservoir has a strong water drive system. So for some reservoirs that are backed up by strong aquifers, which have this infinite acting behavior, you see the reservoir producing for a very long time because the energy of the aquifer is sustaining the reservoir system. So these are things that Havlena and Odeh has made possible. Okay, so the plotting for this, we just concluded application to volumetric undersaturated oil reservoirs. And we see what happens when we make further derivations of what is obtainable for volumetric undersaturated. You have this here, your M, your gas cap, your RPRS, and your WO. Your equation 25 is further reduced to this. We try to put it in Y equals mx plus C. And then when it is plotted, when this is plotted against NP, we are able to estimate our N. We are able to estimate our N, okay? We are able to estimate our N. And then if it is not a straight line like this, what we have here in our hair, we are able to tell the story of what our reservoir could be if it is a B plot or if it is a C plot for volumetrically controlled undersaturated oil reservoirs. Okay, so let's look at volumetric. Okay, this is also volumetric undersaturated oil reservoir. So in this case, if we plot our F versus EO plus EFW, okay, this can also happen. Let's go back a bit. Now, we have F equals N into EO plus EFW. Now, for Y equals MX plus C. So, if we plot our F against this, What do we have? Okay, so if we plot F underground withdrawal against EO plus EFW, what do we have? We have a straight line that goes through the origin. And you have to note that this origin is a control point. Anytime you have a plot like this and then goes through the origin, you know that what you have to have is a straight line. A straight line. So it's like a guiding point for you, this origin. Your plot has to go through through the origin based on Havlena and Odeh estimation. Okay, so your n will be your slope because it is y equals mx plus c. So your f equals n into EO plus EFW. Don't forget. So you plot f against your EO plus EFW. That's what you have here on this plot. And then your slope will be your n, okay, which is your initial oil in place. So we can see how both Schilthius material balance equation and the Havlena and Odeh has made the estimation of n possible. Okay, so let's look at case 2. Case 2, volumetric under saturated oil reservoir. So you know what this means now from my previous explanation of case 1. Case 2, it is volumetric. There is no water inflow. It is saturated. Now it's in the saturated state. Oil reservoir. So you have your pressure has crossed the PB. So pressure has come below. It has hit the PB and probably below. So you have evolution of gas from your oil system within your reservoir. Okay. So what are the main driving mechanism of this type of reservoir where you already have libration and expansion of the solution gas as pressure drops below the bubble point? So the only unknown in a volumetric undersaturated reservoir is the initial oil in place, that's N. And for here, EFW, though, is negligible in comparison to the solution gas because you already have gas now. I remember your CG, which is far, far higher, and your CF and your CW is far lower, okay? But it is recommended to be included because it is not a fully gas reservoir. It is still a oil reservoir, just that it is volumetric one, but that the oil reservoir is saturated. And that's why EFW should still be added to this system. Okay, so let's go. So recollect your equation 25. Don't forget the almighty Schilthius equation. Recollect it. It's quite simple now, and I'm sure some of you can even recall it offhand. Okay, your F underground withdrawal, your oil and your gas component, solution gas component, your gas cap component, your expansion connate water, and rock compaction component, and then your WE. So because it is volumetric, W is 0, don't forget. Because it's not saturated, your RP is no longer equals to RS, it is no longer equals to RSI. So there's a RSI, and as pressure drops, you know your RSI is the solution gas in your reservoir, in your oil, okay? As pressure drops, your RS, part of your RS is released. And what happened? You have RS. As pressure drops again, part of that RS is released, and you have a further reduced RS, okay? So RS has every other pressure, and you have, as this RS is released, then you have the part of your solution gas that is produced to the surface, production at the surface, so which is your RP, okay? Your RP. So this is no longer equal because your reservoir is now in the saturated state. So you have this. So you know the ones that goes out. You have the whole of your F, and this is no longer 0 because RP is not equal to RS. W is 0, affected. You know there is no gas cap, just that we may have a secondary gas cap, but it is not the original gas cap, okay? So M equals 0 because there is no gas cap, okay? M here also equals 0. also equals 0. So you have F equals EHO, everything here, EHO plus EFW plus EFW. Don't forget this is here because it is only this M that is 0. Here, M cancels everything, so making this 0. But here, this is just 0, so you have 1 plus M, that's 1 plus 0. So you see a BOI about 1 minus SW multiplied by this. Okay, so you have F equals N E naught plus EFW. So, but if EFW is neglected, if you maybe some calculations, it could be indicated that EFW should be neglected, then you will have F equals NEO. But if it is not indicated that it should be neglected, okay, we are saying that yes, at this point, the reservoir is now in a saturated state, but the effect of these compressibilities could be minimal, could still contribute, but the contribution could be very minimal. So it may or may not be neglected. Okay. So so this is what we have left. This is what we have. This is a bit of a breakdown of your F, BT high, what you have here, EHO. This is your HEHO left. Your HEHO, if it is in two-phase, if your F is in two-phase, if your EO is in two-phase, then your EFW, that's your BO high, you have this left. So your F equals EO plus EFW, this is the EFW, and this is the EO. If it is this two-phase, okay? So it can either be this or this, okay? EO can either be this or this, okay? Depending on the data you are given. So a plot of F versus EO plus EFW, EO plus EFW, what happens? The plot should result in a straight line going through the origin with a slope of n. If plots, however, turn out to be nonlinear, there could be presence of an unsuspected water influx into the reservoir, helping to maintain the pressure, just like the previous plot that we saw. So as you plot F versus EO plus EFW, you take your slope. Firstly, the control point, your plot should go through the origin. It must go through the origin. And then the slope of that plot is your head. You can estimate your head, okay? And then if your plot now happen to be non-linear, then you should be able to indicate that there is water influx into that reservoir, which is assisting in maintaining the pressure of that reservoir, meaning that that reservoir is not fully volumetric. There is a water body adjoined to it. Okay, so let's look at case 3, which is the volumetric gas cap drive reservoir. Case 3, volumetric gas cap drive reservoir. Now, this is now fully a gas cap drive reservoir. The expansion of the gas cap is the predominant driving mechanism. We understand this now, okay? The effect of water and poor compressibility as a contributing mechanism can be considered negligible because they are far, far lower than CG. CG is far, far, far higher, okay? The accuracy of the pressure data is needed in order to estimate the gas cap size. So because this is a volumetric gas cap drive, the estimation of the gas cap size is of paramount importance to you as a reservoir engineer. Okay, so and because in some cases, yes, the reservoir has a huge gas cap, and then maybe a quantity of an underlying oil. So this makes estimating the pressure data, collection of the pressure data during different tests a bit tasking. Okay, so the accuracy of the pressure data that is taken either on the field or on the field during pressure tests or in the labs, okay, is of paramount importance, okay, because of the oil and the huge volume of gas that you have in question in the reservoir. Okay, so we have seen that CW and CF is negligible, so they go to 0. Your CG is very important to you right now because it's a gas cap driven reservoir. Okay, and the estimation of your gas cap size is of importance to you. Okay, so your M is not equal to 0 because there is presence of gas cap. Okay, this is also not equal to 0. You know why? Okay, because it's volumetric, V equals 0, then CWCF equals 0. Fantastic. So let's go back to our equation 25, which Havlena and Odeh worked on. So you know the ones that goes to 0 and the ones that stays. Okay, so here, because all these our C's are 0 now, so this goes to 0. This goes to 0 because this multiplies this, so EFW now is 0. W is 0. So we have F equals N into EO plus MEG. Okay. M here is not equal to 0. Okay. M here is not equal to 0. M here is equally not equal to 0. But because this and this are 0, okay, that's why this goes out. Okay. So let's go on. So you have, what do you have left? You have equation 36. F equals NEO plus MEG. So you observe that most of the time you have F equals NEO plus MEG. But what EO, EG, and EFW is in each case of a reservoir is quite different. So you should have observed that by now. So you have to know, if you are asked to use Havlena and Odeh derivation, you have to have the information of what case of reservoir are you dealing with, so that you don't do the wrong plot and use the wrong plot, or do the right plot and use the right plot to explain the wrong type of reservoir type. So you have to know the reservoir type, have to know the drives, and then your knowns. Okay. So your F here, this is what your F is, what you have left in your equation 25. If it is, you are given the two-phase two-phase data, this is what you will use, or you are asked to estimate it, and then you have this. Your HEHO becomes this, if it's a two-phase, okay? And this is your BG. This is your BG. BOI, BGI, BG over BGI minus 1. I hope you understand this from here. BG over BGI minus 1. Okay? So you have three unknowns. You have N is an unknown. Okay, so you have three possible cases in volumetric gas cap drive reservoir. N is unknown and M is known. So in this case, you don't know the initial oil volume, but you know your hem. So this is a volumetric gas cap drive reservoir. Okay, so N is unknown, the portion of the oil, initial oil, okay, in your reservoir, but M, the gas cap size is unknown. You have N is known and M is unknown, and case 3 whereby both N and M are unknown. Okay, so let's go. So you have your derivation from Havlena and Odeh. So if you plot it, also it goes through the origin. You have the slope. The slope estimates your N. So you plotted F against EO plus MEG. So in this case, M is known. M is known, so you'll be given your M. Okay, so so your F against this gives your N. Okay, gives your N. The estimate at F at various times, then you can now estimate your F at various times as a function of the production, NP and RP data given. So that will be quite easy for you because you've already obtained your N, so you can always slot in your N and obtain your NP and your RPs. Okay, so case 2, where M is unknown and N is known. So you rearrange the equation to give EG versus F over N minus EO. So you plot you plot F over N minus EO against EG. So this equals Y equals MX. Your Y is F over N minus EO. This actually should be F over N minus EO versus EG, okay? Where M is unknown, okay? So you have, if you rearrange this, you have M equals F minus NEO over NEG, okay? So the point through the origin, the plot also goes through the origin. Your slope is M. Don't forget that your N is known. Okay, so you'll be given your N. Your M is unknown, so you still rearrange. Okay, you rearrange, and then you have F over N minus EO plotted against EG. While your M is still a M. M is your slope. M is your slope, which is still your M. Gas cap size, your slope. Okay, so that is when N is known and M, your gas cap size, is unknown. Okay, then your case 3, where you have M and N are unknown, both of them are unknown. What happens? Likewise, your equation 36 could be rearranged. You have F over EO, and this time around, both M and N are unknown. So you have M plus Mn EG over EO. Okay, so it will be F over EO is Y equals MX plus C. This is your MX. MX. Your M is MN. Your slope is MN. Okay? Your slope is MN. Your X is EG over EO. And your N is your intercept. So in this case, you have intercept. So this is MX plus C. Or you say Y equals C plus MX. Okay? So you are plotting F over EO versus EG over EO. EG over EO. Okay? So your M, so on obtaining your N, now this does not go through the origin. Okay? It doesn't go through the origin for a volumetric gas cap. Okay, so it doesn't go through the origin. You have an intercept because already here you see there is an intercept. So your slope, your M, that's your gas cap size. Okay, your gas cap size is slope over intercept. Remember that both your M and N are unknown. So the N is the intercept, and then you can calculate the M from slope over intercept. Okay, because your slope equals Mn, where you have here Mn. Okay, fantastic. There will be examples to illustrate this in another video. Okay, so let's go to case 4, water drive reservoirs, case 4. So in a water drive reservoir, so you can see that this is not an hydraulically, this is not a volumetric reservoir. It is a water drive reservoir. It is hydraulically controlled. There is an aquifer, okay, attached to it. So you have, in water drive reservoirs, Havlena and Odeh also applied their derivations to these types of reservoir. They extended it to it. So here we want to identify the aquifer type. We want to characterize the properties of the aquifer. Is it a strong aquifer, a weak aquifer, a partial aquifer? So there has to be an accurate description of the aquifer. How would the reservoir perform in the future? Okay, what reservoir management tools have to be put in place? Okay, so an accurate description of the aquifer is needed for future reservoir performance and its management. So this is key in water drive reservoirs. So Havlena and Odeh extended their work to these types of reservoirs in order to be able to tell the type of aquifer, characterize the aquifer, and give a description of future reservoir performance and management. Okay, so what do we have here? In a water drive reservoir, M is definitely 0. Okay, so there's no case of gas here. M is 0. And EFW is also far less. It's far less because this is energy due to rock compaction and connate water expansion. Okay, so it's also quite less because there is a high energy from an adjoining aquifer. Okay, so this energy is quite low compared to energy from our water body. So we have back our equation. EFW is neglected because water and pore compressibility are small, and because the pressure drop appearing in EFW is reduced compared to reservoir pressure maintenance from the water influx. I believe you understand this. Okay, we come back here. So if EFW goes, we know that EFW goes, yeah. If you go back to equation 25, you'll see that the M is 0. We're saying that EFW can be neglected. And then what happens? Our WE stays in this case, in case 4. WE stays because it is not a volumetric reservoir. It is an hydraulic reservoir. Okay. And 1x, our M, EG also goes because M is 0. M is 0. No case of gas or gas cap in this case. So we have, as you go on in your reservoir journey, you're going to be learning these water efflux models. I'll probably also do some videos in this respect in order to explain the port model, port aquifer model, the Schilthius steady state model, and the Van Evangel and Ost model. Okay, all very interesting models, your reservoir journey. Please don't forget all what we have learned in this video from part 1 to part 2 to part 3. In summary, the generalized material balance equation, it is needed for us to understand the MBE from Schilthius. We did a great job in coming up with a model, a tank model, which shows the underground withdrawal with all what is obtainable within a reservoir system, the energy obtainable within the reservoir system, balancing them and showing that it is a zero-dimensional model. And then we've been able to see from part 1 to part 3, the energy drives. We've been able to connect them to our MBE. We saw the assumptions of MBE, the Schilthius material balance derivation itself in the part 2 of the video, and the Havlena and Odeh application to the Schilthius material balance equation. So it has been a wonderful session on MBE. There'll be another video on examples which illustrates all what we have learned from part 1 to part 3. So I'll see you in this video. Please like, share, and subscribe. Thank you very much.